And we're back with another one. Long time no see. I wasn't even looking at the camera just now, but looking at the small Jhevon on the screen. Somehow I'm thinking that's you. Yeah, we're back at it again. Here's another lecture. Just decided to run a marathon today, and because we're on the roll. We talked about some interesting things last time. Hopefully you found it interesting. I think it's interesting. Went a little bit over time last time, totally lost track of time. I will not do that again. Okay, so I am making a note of the time. But even in the last lecture, we had some technical difficulties. I had to restart, so I totally just lost track of what I was doing, just kept talking way longer. It's one thing that's nice about having classes in person is that whenever you're running over time, the students let you know. You just start, you hear like books going into bags, zippers going around, very kind of passive aggressive. People like packing, like, Jhevon, I got places to go. Yeah, no one was there. It's very quiet here, so I didn't know. I didn't realize I was rambling on for too long. Let's keep things a little bit tighter in terms of time this time, and let's continue. So we are going to do that whole sharing the screen thing again. And like I said, I think it's a little less glitchy for me to not show video here. You guys know what I look like, so hopefully me disappearing for a while won't cause you to freak out too much. This was what we were covering last time. We were attacking the area problem. So last time we learned about how we would actually go about finding the area of irregular shapes. So just to give you a quick summary of what we spoke about last time. Okay, so we have an irregular shape. We want to know how to find out how much space it takes up. This is called the area problem. How much space does this random thing that I'm looking at take up? The idea is slice it into smaller shapes that we know how to find the area. To get our math to work out very nicely with this thing, we put it on the XY plane, slice it into smaller strips, and put rectangles below the curve. Technically, they could go above, but the idea is we're using rectangles to approximate the area under the curve. Once we actually know how to find the area under a curve, then we can definitely step backwards and use all that knowledge to find the area of the original thing. Now, how we do that is we dissect the interval under which we want to find the area into a bunch of smaller subintervals, each of which length has delta x, which is b minus a over n. And then we choose how to erect our rectangles on these subintervals using a variety of methods. One was the left-hand rule, the right-hand rule, the midpoint rule. Ultimately, the goal was the same: approximate the area under the graph using the areas of these rectangles. We also saw specifically how to actually do this by going through several different problems where we actually approximated the area under the function x squared plus 1 on the interval 1 to 5 using the left-hand endpoints where we pick numbers on the left side of the interval. We also used the right-hand endpoints where we pick numbers on the right side of the interval. And we use the midpoints where we pick the numbers smack dab in the middle of each interval. We use these guys to approximate the area under the curve. We explained what the difference in the answers were, why they looked the way they did, and that's kind of where we ended up. Now, we also talked about the idea of finding the exact area under the curve. This is us just letting n go off to infinity. N is the number of rectangles we're using, which is equivalent to the number of subintervals we're using. And so the idea is if we use an infinite number of rectangles, theoretically, this will give us the actual exact area under the curve, because all these little spaces and crevices that we're missing with the rectangles, they'll all get filled in. That is the idea. Once we have that notion, we have a whole new notation to talk about it, right? Because essentially, this guy is the solution to the area problem. So it's kind of like how when we found the derivative was the solution to the rate problem, it required a whole new set of notations. We had the prime notation and the Leibniz notation because it's really important stuff. And so we want a new mathematical way to talk about it. So this guy here is called the definite integral. This is an integral sign, the integral from a to b of f of x dx. That is basically called the definite integral from a to b of f of x. It is it is actually what the area underneath the curve f of x is, under in quotations. We'll talk about that in, would I get to that today? Very soon, if not today. So that was, this is the actual guy that solves the area problem. Now, what we did in these calculations was we approximated the answer. We were basically approximating what this thing would have calculated for us, right? Because I didn't really show you how to calculate with an infinite number of rectangles. Today, we are going to rectify that. At least we're going to make a lot of headway on rectifying that. This brings us to the next section, which is called the fundamental theorem of calculus, a very ambitious title for this section. Of course, by the end of this section, which I'm not sure it's going to be by the end of this lecture, if not by the next lecture, we are going to discover a theorem that's called the fundamental theorem of calculus. It's going to be a big deal, and it's going to tie everything together. But for now, we are going to talk about antiderivatives, the antiderivative of a function. This is where we're going to start today's lecture. Now, at first, I just want to come out the gate and just say, for a while, we are going to talk about stuff that would seem to have nothing to do with what we were talking about in the beginning of chapter 5. So last time we were talking about areas and using rectangles to approximate areas on the curves, and we were using Riemann sums and left hand and right hand and midpoint, and we had all this stuff going on. Now I'm going to talk about antiderivatives. And at first you're going to like, it's like going out to left field. Like, what are you even talking about? How does this relate to anything? But I promise you eventually we'll come back, we'll tie it all together, and I will show you the significance of these things that I'm going to talk about right now. But for now, just follow me. It's going to be new stuff, new definitions, new ideas, but hopefully you can follow me here. So let f of x be a function. The antiderivative of that function is another function such that if I were to differentiate that function, I get my function. So little f is a function. The antiderivative is a function big F such that if I take the derivative of big F, I get little f. So big F is called the antiderivative. So let's actually get used to that terminology. For example, what is an antiderivative of f of x equals x squared? In other words, we're on green. I don't want green. Black. In other words, what is a function big F of x such that if I were to differentiate that guy, I would get x squared as the answer? Now, take some time and think about this, maybe even pause the video, try to come up with an answer. What do you think I would differentiate to get to x squared? Now, of course, when you're differentiating something like a polynomial, you want to get the result of a polynomial, you expect you have to subtract 1 from a power. So starting out with an x cubed would make sense. If I differentiate that, I would get 3x squared. Now, because I only have x squared, what I'd want to do is I would actually divide by that 3. So this function actually this function actually makes a lot of sense. This guy is an antiderivative. Since, how do I know it's an antiderivative? If I were to differentiate it, differentiate a third x cubed. That would give me 1/3, because we leave the constant, differentiate the x cubed, 3x squared. The 3's would cancel, and I would just get x squared as the answer. So this is a function that if I differentiate it, I get x squared. Therefore, this guy is called an antiderivative of x squared. It's the guy that if I differentiate it, I get x squared. Okay? Now, I want to talk about the fact that I used an here, an antiderivative. That's very suggestive. It's actually very important that we're talking about an antiderivative. Okay? So what would the significance of that being? So here's a follow-up question. Can you find another? Can you think of some other function that if I were to differentiate, I get x squared? Think of something else besides the 1/3 x cubed. Anything different to 1/3 x cubed? Could you come up with something? Okay, hopefully you thought about that, maybe even came up with something. Here's another one. 1/3 x cubed plus 5. This is an antiderivative, right? This is an antiderivative again. How do you know it's an antiderivative? Well, if I were to differentiate 1/3 x cubed plus 5, then the derivative of this part is x squared. The derivative of that part is 0. So I get x squared. So this is a function that if I differentiate it, I get x squared. It's an antiderivative. Could you come up with another one? Sure. 1/3 x cubed plus 7, or 1/3 x cubed plus 9, or 1/3 x cubed plus 37.3. I think you're getting the idea. The idea is if we take 1/3 x cubed plus any constant, here c is a constant, this function will be an antiderivative because the derivative of the constant is going to go to 0, and then the derivative of this is going to give me the x squared, right? So that is why we use an here. An antiderivative of a function is not unique. In general, any function with an antiderivative will have an infinite number of them. Literally, the antiderivative plus any new constant, and there's an infinite number of constants, will lead to another antiderivative. So let's, this needs to some new terminology here. Suppose the constant is not in play. So big F is an antiderivative with no constant terms. So in this part, that would be the 1/3 x cubed. Then this expression, big F of x plus c, this plus a constant, is called the general antiderivative, okay? So in other words, this one here would be called the general antiderivative. Okay, because it's a plus c, it means that you can kind of substitute anyone here. And in fact, the terminology, because you can substitute anyone for the c, it's kind of arbitrary, we shall say. The c is called the arbitrary constant of integration, right? And the big F in this general form, that's called the primitive. Now, you don't really need to know what the names are. It's just that if I mention these phrases, I want you to know what I'm talking about. By the way, it's called the constant of integration because the process of computing an antiderivative is called integration. So it's an arbitrary constant of integration in parentheses, okay? So we're going to look at ways. I mean, x squared probably wasn't that bad for most of you. But if the function was more complicated, it's figuring out who I had to differentiate to get that is a lot harder. And in fact, in general, that is the case. In Calculus 2 and higher is where you learn about how to compute antiderivatives and applying them and what does it mean. And that course is actually a lot harder than Calc 1. So it is actually in general harder to come up with an antiderivative of something than it is to come up with a derivative of something. But that being said, the process you would have to go through to actually compute an antiderivative, we call that process integration, okay? So that's where this comes from. Now, again, because it's a very important, finding an antiderivative, it's a very important idea. Finding a general antiderivative is also a very important thing. So we actually have a new notation for that. Every time there's something super important, muy importante, we would like to come up with a new notation to represent that thing. And here is the notation for the general antiderivative of a function. the general antiderivative of a function f of x is denoted by this symbol, an elongated s, f of x dx. That's what that guy is called. Now, at this point, the more, shall we say, perceptive among you are like, that looks awfully familiar, that notation. I mean, that's pretty similar to the notation we had for the definite integral. What is up with that, Jhevon? And for those of you who noticed that, I'm glad you asked. Yes, it is quite similar, isn't it? If you go back to the last lecture, look at this guy. That looks almost the same. The difference is we don't have these numbers here, but otherwise everything is exactly the same. So yeah, that is a curious coincidence. Or is it a coincidence? We shall see. This guy is called the general antiderivative of f of x. We use this symbol, and another way to say this, aka the integral of f of x. Now, if I want to emphasize that I'm talking about the general antiderivative, we might say the indefinite integral. Now, why is it indefinite? Well, it's because the plus c, this part makes it indefinite. You don't definitely know what the answer is. You don't know exactly which antiderivative you'd really want for a particular situation, okay? So the most general antiderivative for x squared is a third x cubed plus c. That guy is called the integral of x squared, right? So in other words, I could say, that should be 2 words. I could say the integral of x squared is a third x cubed plus c, for instance. Okay, so this is the symbol we use for the antiderivative, which is kind of a foreshadowing of a connection to come. We'll talk about that in a little bit. And this is called the integral of f of x, or the indefinite integral, if we want to be very peculiar. So that's very particular, not particular. Oh, I mean, yeah, let's be peculiar, why not? Okay, indefinite integral of the function is the same as the antiderivative of the function. And so by the above notation, here's how it would actually look for us to write something down a little bit more generally, right? So we can write that notation. So for example, to write this guy here, when I say the integral of x squared dx is x cubed over 3 plus c, this is basically me just writing down this sentence in mathematical notation. The integral of x squared dx is x cubed over 3 plus c, aka the antiderivative of x squared is x cubed over 3 plus c, or the general antiderivative of x squared is x cubed over 3 plus c. This is called the indefinite integral, or the general antiderivative of this function. That's the symbol we use to represent it, and that's how we would say it, okay? Another word on notation is, again, the dx part is very important for you to notice. The dx, that part is called the differential, as I mentioned last time. It is always, maybe I should put that in bold. It is always written to the top and to the right whenever it does appear. So for example, here's the antiderivative of 1 over x squared dx. Notice that the dx is on the far right of this notation. Here, it is to the top, and to the far right of that notation. So this is actually writing the same thing. I just put the dx on top. This is incorrect. No, here's your dx is, the dx is in front of the 1 over x squared. You never want the dx on the left. Here, your dx is in the denominator. That is also, come on, what are you doing, man? Pay attention. Like if you write your d's on the left or in the bottom of anything, I'll know you're not paying attention. The dx is always, always written to the top and to the right. Now, in Calc 1, you're probably not going to realize the significance of this, and you're probably not even going to have to worry. You're probably not even going to want to worry about, does the dx even matter at all? This is not true. The dx matters, and its position actually matters. And in the next section in 5.4, I want to say, when we talk about substitution, you're going to realize that the dx needs to be there because you're going to have to take account for the dx later on. But that being said, the dx, the differential, it's always written to the far right of the notation. Okay, it's never to the left, it's never at the bottom, it's always the thing that's to the farthest right. So it's the integral sign, the function is in the middle, the dx is on the right. Or potentially the dx is on top of the function and nothing comes after that point. Okay, so that's very important, because you know, it's not just important for you to know the math, you have to look cool while writing it down and sound like you know what you're talking about, and everyone should know that you know what you're talking about. Okay, so that's just a word on notation. Now, let's talk about some integration formulas. Rules of thumb. For those of you who couldn't see that this would have been the answer, how can you come up with strategies or formulas to find some antiderivatives, at least in some basic cases? That's what I want to talk about now. The following are immediate based on the ideas that I mentioned here. So formulaically, one way you want to find an antiderivative is to reverse the process of a derivative, right? You want to find something that if you were to differentiate, you would get the thing that you're looking at. So what you want to do is take what you're looking at and kind of reverse the process of integration, of differentiation. So this suggests that every differentiation formula is going to be an integration formula in reverse, and it would also give you ideas on how to actually change back to the antiderivative. That being said, we have these three formulas that are pretty much immediate. So here's one thing. So in order to find this is called the power rule for integration. So let's recall the power rule for differentiation. Right, so remember we took d dx of x to the n. What did we do? We brought the n down and subtract 1 from the power. In other words, what we did was we multiplied by the old power, as in the guy that we started with, and then subtract 1 from the power. To get the new power. Okay, and that's how we kind of found the derivative. What we want to do is reverse this. How would you reverse it? Well, instead of multiplying by the old power, you would divide by the new power. And add 1. To get the old power back. Right? So where we had multiplied by the old power, we're now going to divide by the new power. And where we subtracted 1 from the power, we're going to add 1 to the power. And so to reverse this process, we get something like this guy right here. Right? So we added 1 to the power. So this is basically saying, if I want to compute the antiderivative of x to the n dx, what I'm going to do is I'm going to add 1 to the power. I'm going to divide by that new power, of course, plus a constant. Now, obviously here, your n cannot be minus 1 since you would divide by 0. Okay, so this rule works as long as your power is not minus 1. Now, if your power is minus 1, essentially now you have x to the minus 1, which is 1 over x. And we actually have a rule for 1 over x, right? So this guy deals with that situation. So this is what I mean. It covers the case where the power rule, it covers the case in the power rule when n equals minus 1, because we can actually use this. We would divide by 0. And it turns out that this one is ln. How do we know that? Well, we actually know that the derivative of ln of absolute value of x is 1 over x. I derived this for you guys a long time ago. Now, we also know, by the way, that the derivative of ln x is 1 over x. But this covers more cases. Okay, so for ln x, your x needs to be positive, but with the absolute value here, your x is allowed to also be negative. So this one covers a lot more cases. So this is the version of the formula that we like the most, because it covers the cases when x's are negative as well. The only one these guys don't work with is for x equals 0 specifically. But if your x equals 0, the original case will deal with it, because you plug in 0 here, you just take the antiderivative of 0, which is just a constant. So this will actually work when your x is 0. So once your power is negative 1 and, once your power is negative 1 and you're not allowed to divide by n plus 1, it's just an ln. This is, again, this comes from the idea that we can figure out the formulas by reversing the process. Of taking a derivative. Okay, so because I know the derivative of ln x gives me 1 over x, the antiderivative of 1 over x gives me ln of absolute value of x. The absolute values are actually pretty important. Okay, so if I were to ask you the antiderivative of 1 over x dx, your answer should be ln of the absolute value of x plus c. It's very important that you put the absolute values, okay? Now, what is the antiderivative of e to the x? Well, e to the x plus c, right? So we knew that the derivative of e to the x is e to the x. So the third formula is pretty easy. To differentiate e to the x, well, that's e to the x. Okay, this is plus c. Right? So this says that if I'm taking the antiderivative of e to the x, meaning if I this side and I want to figure out what function gave me this to begin with, well, himself gave me that. Plus potentially a constant that when I differentiated it died, right? So yeah. So we have these 3 basic rules, very important rules. In fact, they should be memorized. You need to memorize these formulas. I will expect you to know them. Okay, so the guy's in this box here. Okay, now there's a variation on this formula here that I think is more useful in more cases. This is the antiderivative of e to the kx dx. It's going to be 1 over a k e to the kx plus c, as long as your k is not 0. So let's do some quick examples of that. For example, I can ask you, what is the integral, or aka the antiderivative, of e to the 5x dx? Well, according to this formula, it's 1 over 5 e to the 5x plus c. Plus c, also very, very important. Do not forget the plus c on an indefinite integral. Or what is e to the minus 7x dx? Integral of that, or the antiderivative, is minus 1 over 7 e to the minus 7x plus c. What is the antiderivative of e to the minus pi x dx? Minus 1 over pi e to the minus pi x plus c. Hopefully you're getting the idea. So if it's e to a constant times x, it's just 1 over constant times e to the times the original function. Okay. Now, why this is true, we'll talk about why this is true later. But that's basically the idea here. Okay. Now, so there's these basic rules which you're going to have memorized next time you see me. So I'll give you guys the notes and you'll read this and you'll have it memorized. Let me actually, so you can actually see that properly. Okay. Now what I want to do is with these guys, I want us to practice using these rules because that's going to be very important. So let's actually get to practicing using these rules. So for example, so here's a problem. Find the integral of x cubed, aka find the antiderivative of x cubed. What I want you to realize is to notice this looks like the antiderivative of x to the n dx, where in this situation your n equals 3. And in particular, that it's not equal to -1. So basically, whenever you see something, the first thing you're going to try to do is you're going to try to match it up with one of these forms that I gave you. Which one of these formulas does the thing I'm looking at look like the most? So I can apply these rules. Now, clearly, formula 1 is what this one looks the most like. So all I'm going to do is apply formula 1. So this is going to be add 1 to the power and divide by the new power plus c. Do not forget the plus c. When there are no numbers on this integral sign, you have to put a plus c. In other words, this is x to the 4 over 4 plus c. And that's the answer, i.e., the antiderivative of x cubed dx is x to the 4 over 4 plus c. Okay? Are we okay? Let's do another one. So B. So here's the next example. What is the antiderivative of the square root of x? In other words, what function do I have to differentiate so that I get square root of x as the answer? Now, take some time to think about it. Write that down, antiderivative of square root of x. Look at these formulas and tell me which one you think. So maybe write this down. Take a few seconds, pause the video, try to tell me what you think the answer is. Okay. Hopefully you have some idea here. Now, here we have the square root of x. Now the thing is, you have to say, well, who does that look like in this list of formulas? Does it look like an e to the x? Well, no. Does it look like a 1 over x? Well, no. Does it look like an e to the kx? Well, no. So now you're pretty much down to this by process of elimination. This is the only other formula that it could possibly look like, but it doesn't quite look like that, does it? There's a radical symbol. So now the question is, well, could I get it to look like one of these formulas? And I'll talk about this later on, of course, when I always give you guys strategies after I go through something with you. So the first step is to just kind of see, does it look like a formula that I have? And this one looked directly like a formula that we had, so we just applied it. The next thing you're going to want to think, if that's not the case, can I finagle the thing that I'm looking at to make it look like one of the forms that I have? And hopefully you would realize that, yeah, in this case, you can do that. Radical x is just x to the 1/2. So this looks like formula 1 again, x to the n, where your n is a half in this case. How do we deal with that? Well, the same way we deal with all situations where your n is not -1. You add 1 to the power, and you divide by the new power, plus c. Do not forget the plus c. So this is going to be x to the 3/2 over 3/2 plus c. Now, of course, keep, change, flip, all that good stuff. To divide by a fraction means to multiply by its reciprocal. So it's 2/3 x to the 3/2 plus c. And that, ladies and gentlemen, is the antiderivative of the square root of x. And of course, by the way, for all of these, you could even check if you want. Now, of course, you don't need to put the plus c in the check, but what would the derivative of 2/3 x to the 3/2 look like? Well, the constant would stay because of the constant factor rule. The power would come down, 3/2, and then you would subtract 1 from the power. Now, there, the 3 cancels, the 2 cancels, and 3/2 minus 1, well, that's a half, isn't it? So, yep, that's the guy we wanted. This is the antiderivative. Okay. Now, hopefully that's clear. Let's look at this one. All right. What do you guys want to do here? Take a second, think about this one. Okay, so some of you might have got this right. Some of you might have made an error. So let's talk about that. So, warning. Let me just lead with that here. If you want to find the antiderivative of a division, right? Let's say there's one function on top of another one. It is not just finding the antiderivative at the top and then finding the antiderivative at the bottom, right? This is wrong. That is not what you want to do. In the same way with derivatives, it didn't even work with derivatives, right? If we had a division and we wanted to take a derivative of that division, you could not take the derivative of the top and then the derivative of the bottom and then stick them together. Here we're reversing the process. So if it couldn't work going forwards, like something like that isn't going to work going backwards. In fact, going backwards, it should be even more complicated, right? You're walking backwards here. So something like that is not going to be the case. So if some of you potentially what you wanted to do is you found the antiderivative of x plus 1, and then you divided that by the antiderivative of x. This would be an incorrect thing to do for this situation. That being said, if you actually tried that, maybe pause the video right now and come up with a different way to approach this problem. Okay, so here's how we want to do it. So again, remember, the first step is, does this look like any of the formulas that I have? And the answer is nope. All my formulas looks like x to the n, 1 over x, e to the x, e to the kx. This does not look like any of those. Second quick thing, can I finagle it, rewrite it, simplify it, do something to it to make it look like some of the forms that I have? And the answer for this one is yes. In fact, using algebra, I can just, of course, that is equal to that. I can divide into each. Now this first one, x over x, is just 1. Now here is something that we are allowed to do, which you might not be sure if you're allowed to do it, but I'm going to tell you now that it's okay. Derivatives distribute across sums, right? So it turns out as with derivatives, antiderivatives distribute across sums. And again, this should make a lot of sense because you're reversing a process. Now, if you could do one thing at a time when going forwards, then all you have to do to go backwards is just undo the things one at a time. So in other words, if you have the integral of f of x plus g of x, and you wanted to find the antiderivative of that, you could do one at a time. So in other words, this would be like, I could do this one, and then I can do that one. Now, ordinarily, you don't have to write this line down, but I just want you to know in your mind, this is how you're thinking. Just do them one at a time, once there's a plus sign in between. If there's a multiplication or division, you're out of luck. You cannot do one at a time, as I said here. But with addition and subtraction, you can. Now, of course, the 1 two ways you can look at this. Of course, you just know that the derivative of x is 1. So that automatically tells you the antiderivative of 1 should be x. Okay, so you can just know that by heart. Another way is to just realize that, or just realize that 1 is really x to the 0. So this is an x to the n where your n is not -1. You could actually just add 1 to the power. And then divide by the new power. So you still get x. So this is an important fact that you should know in general, that we can do it one at a time. And knowing how to find the antiderivative of 1 or the integral of 1 is something else you should just know how to do. You should know the answer is x plus c. So this one we can deal with. He is in fact under the formula integral of x to the n. And this one, the 1 over x, do we know what that is? Yeah, that's the formula right here too. Therefore, this is x plus ln of absolute value of x plus c. The absolute value is important. Okay, do not forget the absolute value. It's important. Okay. Yeah, so that's your answer for this one. Now, hopefully that was clear. Let's keep going. How about this one? Take some time to pause. Do that. Now, with any luck, hopefully you got something like the following. So again, do have forms that look like this? If you look at the forms that I had you write down, then the answer is no, at least not right away. So now your idea is, can I rewrite these to look like a formulas? The closest thing that these guys would look like is the x to the n. The first one is the x to the half. The second one, I can bring the x squared up to the top, and so that would be x to the minus 2. And now you might be worried about the 3 times the x to the minus 2. How can I deal with the 3 times the x to the minus 2? Well, it turns out, again, if you are taking derivatives, you ignore constant factors and just worry about the function part. So again, if there's a constant times a function, to reverse the process, it makes sense that you can ignore the constant part and just do the other part. So as with derivatives, integrals have a constant factor rule, i.e., if I want the integral of a constant times f of x, I could leave the constant alone and find the integral of the f of x. Okay, so I can factor constants out and just worry about the function part. So this part, I can just think of it as, again, the integral would distribute across the sum, and at the same time, I can factor the constant outside of this one. Now, you don't need to, again, you don't need to write this line down, but you do need, that's the way you'd think about it in your head. So for this one, again, add 1 to the power, divide by the new power, plus this one, you're going to add 1 to the power and divide by the new power, plus c. Always a plus c when you have an indefinite integral. And so this guy is 2/3 x to the 3/2 minus, well, 3 over x. And again, you could double check this. You could actually differentiate this and see that you would get this. You would actually get the original. I shall leave it to the reader to verify. Let us get through these other ones down here. Let's get through these 2 examples here. So there's that guy. Again, pause, try that. Integral of 3e to the x minus 7 over x cubed. Okay, now hopefully you took a shot at it. So here's what the answer would look like. Again, this kind of looks like directly like one of our formulas. I'm not too worried about that, but this guy doesn't. I would actually want to rewrite that to look like a formula. And again, you can factor out constants and separate these guys. But like I said, you don't actually have to write down a line like this. If you jump from this line to the line I'm about to write, I'll take your word for it that you understood how things actually broke apart. So we have 3 times the antiderivative of e to the x. And what's that? Well, it's e to the x. That's a formula. Minus 7. Now this is going to be, of course, x. You add 1 to the power, divide by the new power, plus c. In other words, this is 3e to the x plus 7 over 2 x to the minus 2 plus c. So that would be that antiderivative. And again, you can check. If you were to differentiate this, you would get that. Let's look at another one. Last example here. And hopefully after going through these 6 examples, you'll get the hang of it. But of course, there'll be many more examples for you to do in your homework and otherwise. Yeah, what about this one? pause the video. Tell me what you think. So again, don't wait for me to do it. Actually try it on your own. This one, I can think of it as 4 times 1 over x. It's a constant times something that I know how to find it. This one is minus a third times e to the 2x. And these guys, I have a rule for that, and I have a rule for that. This is e to a constant times x. We had a rule for that right here, rule 4. And this one is rule 2. So this one here is rule 2. This one here is rule 4. So again, I can think of this as 4 times 1 over x dx minus a third times e to the 2x dx. Don't have to write that down. But what is the antiderivative of 1 over x dx? What's the integral of 1 over x? ln of absolute value of x. And e to the 2x over 2. Which when I put the over 2, it multiplies by the over 3. And again, absolute values are important. Do not forget the absolute values. So that's just a quick set of examples there where we're computing antiderivatives or indefinite integrals. So I can call this the integral of x cubed or the antiderivative of x cubed. The integral of the square root of x is this, and I'm finding some integrals. And this all relies on you guys knowing and applying these 4 formulas. And the idea is either what you're looking at is going to look directly like one of these formulas, or you're going to have to finagle it, do a little algebraic simplification, do a little move things around to try to get it to look like one of these formulas. And if that works out, great. Now, life is a little bit more complicated than that. Not everything is going to be like these, where you can just shift things around a little bit and get to the answer. In the next section, section 5.4, we will actually talk about situations where you have to find integrals that are a little bit more complicated. That being said, I'm pretty sure, because I told you guys that I was going to pay attention to the time, pretty sure we're out of time here and I don't want to run over too much. So we're not done with this section, but I am going to stop here. We're going to talk about some more things later on. So I'm ultimately going to talk about the fundamental theorem of calculus, all that good stuff, all that. And then we're going to do more examples. And of course, when doing that, I'm going to talk about like the meaning behind all this. What does it all mean? And all that good stuff. Did I have more to talk about in this section? No, I think I just left space to actually do those examples. Okay, so we'll stop there. Hopefully that was clear. A little less rambling than last time. We just kind of got straight to the point here and learned how to do these calculations. A lot of it depends on these rules. And the rules themselves just depend on you reversing a derivative, because that's what an antiderivative is all about. So this is just a new idea of finding an antiderivative, and hopefully that's clear. I will again post the notes of everything. A link to the notes will be in the description. Of course, if you have any questions, you can drop them down in the comment section, or you can email me and we will deal with them. That being said, we're going to wrap up there. I think we ran a few minutes over, but it's not like last time we ran like 20 minutes over, or maybe even a little more. So we'll stop there. We'll pick up with the next one, and hopefully it's going to be a lot of fun. Pay attention to this lecture, see if you got it and everything's okay, right? Until then, we will stop for now. Stay home, stay safe, keep studying, and I will see you guys around next week. Ciao.